All right, welcome back, guys. So now we're going to analyze a couple different classes of projectile motion problems, starting with the easiest case, which is the zero launch angle case. That just means we're launching a projectile perfectly horizontally. Consider a diver diving off a diving board. So on a diving board, you're going to get a little bit of bounce from the diving board. You're going to bounce up before you fall back down. So your launch angle is some speed that looks like it's going up this way with a greater than zero launch angle. What we want to do is simplify this a little bit. We want to take all that initial y component of the velocity out of the equation, literally, and we want to consider a diver diving straight horizontally off of a cliff, where their initial y velocity is 0 and their angle is thus 0. So there are a couple things that we know about zero launch angle problems, namely the initial velocity in the y direction is 0, the initial starting x position is 0, the initial starting y position is some height of this cliff h. There's a bunch of other things that we'll identify when we do this example. So let's say a diver jumps horizontally off a cliff. Let's say she goes at 3 meters per second horizontally. The cliff is 20 meters tall, so h is 20 meters. When the diver is 5 meters above the ground, we want to find the magnitude of her velocity vector, the angle theta of her velocity vector, and how far she has traveled horizontally. So when we look at this picture, if we go over to this example, we want to figure out a couple things. One, her motion not quite at the end of her dive. So this is going to be about y equals 5 meters. Not quite when she's at the ground. So we want to find, one, her speed at the very end. We also want to find the angle in part B. That's going to be this angle, the angle below the horizontal of her velocity vector at the very end of this motion. And at the point where she's 5 meters above the ground, we also want to find how far she's going horizontally. All right, to start this problem off, the first thing we generally want to do when solving problems is draw a picture. Luckily, in this particular case, that's already been done for us. The second thing we want to do is identify our knowns. Then we can identify our unknowns and figure out what we need to solve for. There's a bunch in this problem. I'm going to go ahead and identify all of them for you off the bat, but what might happen is you can identify ones that you notice and then go back when you do step 3, which we'll do down here. That's where you actually plug in our knowns to the kinematic equations and then solve for what you want to find. Sometimes when you're writing down the kinematic equations and plugging stuff in, you'll remember another known that you might actually have from the question prompt. Okay, let's write down a couple obvious ones. One, the 3 meters per second given in the problem. That's v naught is 3 meters per second. Additionally, this is the entirety this is all in the x component. So v naught x, which we'll see in one of our kinematic equations, that's what that guy is. Additionally, we start at x0 equals 0 and y0 equals h equals 20 meters. We have the final y position is 5 meters. We're going to call that y. And we have a couple other things. We know that theta is 0 degrees. We know that ax, a in the x direction, is 0 since nothing is affecting this guy in the x direction. He's only accelerating in the y direction from gravity. And we know that ay is minus g is minus 9.81 meters per second squared. That's how projectile motion works. This guy only accelerates in the negative y direction. We also know a couple other things. We know that v naught y, we already said v naught x was basically the entire speed v0 because it's only going in the x direction, it's just 3. V naught y, similarly, since it's launched horizontally, is 0 meters per second. Now let's see if we got them all, and we will write down our kinematic equations and plug in. So we've used a couple different classes of kinematic equations. The two basic ones were this guy, which was one that was written in terms of time for an object that has constant acceleration. The other one we used was this guy, which wrote final velocity in terms of the initial velocity, the acceleration, and a change in position. You can use either one of these. If you use equation 1, you'll first solve for the time and use that to find the final velocity in combination with the equation v equals v naught plus at. Or you can use the second equation and do the whole thing in one step. Okay, let's try doing it all in one step. So we'll use that second equation. Whenever we're doing a projectile motion problem, we want to separate everything into x and y components. I suggest quite literally writing out an x and a y and saying this is everything that's going on in the x direction, this is everything that's going on in the y direction. The reason I think you should do this is because you have to make things organized. You can't, the goal is not to do things as quickly as possible, writing just a bunch of random numbers on your page. You got to have things nicely organized to keep your thoughts in order. Okay, cool. So we're going to use vx squared equals vx naught squared plus 2ax x minus x0. We know a couple of these things. We know this guy is just 3 meters per second. This guy is 0. We don't know x, but we do know x naught. And none of that matters anyway, because since ax is 0, this entire term is going to go away. And we know that, we wrote that up here. So that means this is vx0 squared, or just 3 meters per second squared. And so if we want vx, it's the same as v0 Great. And that we identified up here when we said that the initial velocity was 3 meters per second perfectly horizontally, which means the x component of the velocity is just the entire initial speed. That's why I'm calling it v0. Alrighty. Next comes the y component. We can move this guy up a little bit. vy. We got that guy. So we know a lot of these. We identified a bunch of things in our knowns, and again, remember, you don't have to write all those knowns on your paper off the bat. What you really want to do is get these kinematic equations down and identify which knowns you might have, and sometimes you might forget to look for them in the problem statement. But we've got vy0, ay, y final, and y initial up in our knowns. And you can check the upper right-hand corner for those. So what are these guys? vy0 was 0. ay was negative g, and we'll do this symbolically for now. Y was known, that was 5, and y naught was h, that was 20. We can rewrite this as 2 times minus g times y minus h, and you can use the negative on the front of g to flip the signs of y and h inside the parentheses. So this becomes 2g h minus y, which means that vy, if we take the square root of both sides, is 2g h minus y. Great. All right, so part A, now that we've found the components, part A was about finding the magnitude of the velocity vector at 5 meters above the ground. Great. Okay, now we've got that guy. Let's do it. How do we find the magnitude? We know that v, the magnitude, is the square root of the x component squared plus the y component squared. So if we do this symbolically, now granted, let's make a special note. You know this. This is 3 meters per second, and you know this. This is 2 times 9.81 times 20 minus 5, or 2 times 9.81 times 15 square root. You can go ahead and calculate a number here and a number here, and you'll get the exact same answer I'm going to get. I'm going to write it purely symbolically. And we're going to have 2g h minus y square root squared. So whatever that number is, and at the end of the day, I ended up getting about 17.4 meters per second. Great. So that's the answer to part A. You also could have done this by using the other kinematic equation with the x equals x naught plus v naught t plus 1/2 at squared, and then sort of combine that guy, use that guy to solve for t, and then use velocity equals initial velocity plus a times t to get that final velocity. Now, getting the angle for part B is actually pretty simple. We know that the angle here, up in our diagram, is going to be the angle below the horizontal, and we can find it by just using the arctangent. We know that theta is going to be the inverse tangent of the y component, Vy, over the x component, Vx, and that's going to get us the inverse tangent of root 2g h minus y over the initial speed v0, and that gets us about 81.9 degrees, which is pretty steep, but it works. Okay, so now we've gotten the angle and we've gotten the final velocity. Now, how are we going to get part C? Part C is asking for how far has she traveled horizontally. And that's an interesting question. So for this, we don't actually want to necessarily use the equations we've used so far. So let's try a little bit of a different approach. Let's first find the time, and then we can use the x velocity to figure out how far it's gone in the x direction. And this is also going to show you an alternative way of solving parts A and B. That's why we're going to do it this way. First, we're going to start back at the beginning. We want to know how far it's gone in the x direction. Let's use that equation of motion. So now that we've got that guy, we can eliminate some things that we know. We know x naught is 0. We know v naught x is just v naught, or 3. We know ax is 0. So we know that x is equal to v naught times t. In the y direction, we have y equals y naught plus v naught yt plus 1/2 ayt squared. And I know this is being a little bit tedious, but we want to be careful the first couple times we do this to get everything right. So we know that the initial velocity in the y direction is 0. We know that ay is minus g. And we know that y naught is h. These are all the things we did in the previous part. So we can plug in that y is h minus 1/2 gt squared. Now, what are we solving for here? We are solving for t. We know y, h, and g values. So the only thing we don't know is t. So let's solve for it analytically. So first what we want to do is we want to say this. This, by the way, the symbol means implies. So we're going to subtract h from both sides. So we have y minus h equals minus 1/2 gt squared. This we can rewrite as h minus y equals positive 1/2 gt squared. Isolate t squared, and we get 2h minus y over g. We can then take the square root of both sides and get this, root 2h minus y over g for t. When you calculate this guy, it should come out to about 1.75 seconds. And remember, if I've made a calculational error, if any of these numbers are wrong, 1, do let me know. And 2, what I love about doing things analytically, purely in terms of variables, is you can always check if it's easier to check if your answer makes sense. And that, by the way, you get that 1.75 by plugging in 20 for h, 5 for y, and 9.81 for g. After we do this, this was the first part. Now, we got to find how far it's gone in the x direction. The position x from earlier is the initial velocity times time, which is the initial velocity times square root of 2h minus y over g. When we plug in the numbers, we have 3 meters per second, 2 times 9.81 meters per second squared, times 20 meters minus 15 meters, all over, oops, and we made a little bit of a mistake there. That's why I don't like plugging the numbers in. 20 minus 15 meters over 9.81 meters per second squared. And once we get that, we should get about 5.25 meters. Awesome. Well, thank you so much for joining us for this rather extended example of a horizontal launch problem. Please do now try the follow-up problem, the all-important follow-up problems. I want you guys to take these seriously, work them with a partner. Let me know if you have any questions, and use this example to try to help you solve those. All right, I'll see you in a couple minutes.